Okay, so we're going to be talking about more linear programming stuff. So we're going to be doing some stuff in Excel. We're going to use Excel for some of this, and we're going to be talking about some of the sort of follow-up questions that you can ask after you get a solution. And we're going to be talking about some of the more difficult problems to formulate. So last time we did the graphical stuff, right? So we had our corner points, we found our maximum profit and so on. These next ones, we're going to use solver, right? So we've used solver already in the course. So there's just some instruction on these slides about adding solver if you don't have it and stuff, but we've already done that. Now, I'm going to show you what the setup is going to be like in Excel. So in Excel, we're going to have all the problem data entered in, and if we enter it in a certain format, it's just going to make things easy. There's going to be some cells that we're going to leave blank for the values of the decision variables that solver is going to act on, right? Solver is going to change those cells in order to minimize or maximize your objective function, right? So we're going to have a formula for that objective function. And we're going to have a formula for the constraints, right? The constraints are things like the total amount of paint used must be less than this number, right? So the right-hand side, this number, is just the number. And we're just going to hard code that in. But the left-hand side, the total amount of paint used, is going to depend on the decision variables. So that's going to be a formula. And what we're going to see is that the formula in step 3 and the formula in step 4 are actually just the same formula. It's just a sum product formula. So we're going to have exactly one formula for this whole sheet, and we're just going to copy and paste it down. And that's it. So this one's going to be really easy on the formulas. So the way the sheet's going to get laid out is going to be like this picture here. Right, we're going to have the headings in the columns, right? Column B is for tables, column C is for chairs, for instance, right? We're going to have our variables there. And then below that, we're going to have the blank spaces where the variables will be. Right, so we have the blank spaces here. And then below that, we're going to have the coefficients for the objective function. And then by doing the sum product of those coefficients with those variables, we're going to get the actual value of our objective function, the profit. And then down here where we do the constraints, we're going to have the coefficients for the constraints. Right, this is like 4t plus 3c is less than or equal to 240. Right, and then this place where there's a 0, that's where we're using the formula to actually calculate 4t plus 3c. And right now, t and c are just blank, right? T and c start off blank. So that's going to start off being a 0. But once solver gets into this, solver is going to act on that to change those. Okay, so this is going to be the setup. We just have to have all our coefficients lined up with all the variables, and then have one formula, which is the sum product formula that'll work for all of these, and then the right-hand side, and then we're ready to use solver. Okay, so yeah, and I'll show you solver in Excel. So I think these are the instructions if you need to refer to them later, but it's going to be easy if I just show you in Excel. All right, we're going to have our objective function, our variable cells, our constraints, but I'm just going to change my share now to share an Excel sheet. Okay, so here's an Excel sheet. Right now it's blank, but if I just put in what we had there, the tables, chairs, I'm just setting it up like it was on the slide. We have the blanks here. This will be where our variables are. We're gonna have the objective function 70 and 50. And then we're gonna have the constraints, which were 4, 3, and then that could be less than or equal to 240. And we had 2, 1, and that had to be less than or equal to 100. And so the only formula we need, right, is the sum product formula. So it's gonna be sum product of these coefficients, comma, these variables, and the variables should be made static, right? Dollar signs there, because now we can just copy that down and all of these work as well. Right? If I look at this one, we're doing some part of these coefficients with the variables. Right? So if you start changing the variables, 1 and 2, right? If you produce one table and 2 shares, then you make $170 profit. You use 10 hours of carpentry and 4 hours of painting. Right? So that's what happens if we start changing these. I'm going a little bit quick, but we'll be doing a bunch of these, right? So we're gonna have a bunch of examples and we're gonna be doing them in Excel. And so you get to see what we're doing here a few times. All right, so in solver, we have our objective. We're trying to maximize it in this case, because in this case it's profit. Which cells are we changing? We're changing the highlighted ones, those blanks. And then now the constraints, we can actually do these in groups, right? Both of these are less than or equal to both of these. Oops. So we don't have to do them one at a time. We can do them one at a time. We can do this is less than or equal to that, this is less than or equal to that. But if we just click OK here, we get both of them. And this checkbox that says make unconstrained variables non-negative, that needs to be checked. I want to double check. You can see the checkbox, right? Sometimes the screen sharing is weird and it doesn't show popping windows that pop up. You can all see the solver window, right?
Yes, Professor.
Good. All right. So yeah, you can. So this checkbox, that's non-negativity, right? That's we can't produce negative shares or negative tables. And then this needs to be simplex LP. Okay, that's the linear programming one. If it's not simplex LP, then certain things we're doing later won't work. If we kept it as non-linear, we'd probably get the same solution. But there's other things that we're doing later today that will not work, that we need it to be simplex LP for. Right? And we click solve and we get the solution. Right? It says there's a solution. Okay, great. This is the same solution we got when we were doing it by hand last time. All right, 30 tables and 40 chairs, making a profit of 4,100. Okay, so like I said, that was quick, but what I want to do now is I want to go to some new problems, not just the table and chairs. We're going to do some new ones. We're going to formulate them, and we're going to solve them with Excel.
Professor, the column D is objective.
Well, the column D has all the formulas. So let's go back to that. The column D has here, this is the objective function, right? Because this row was the objective function row. And then these rows were the constraints. Right, so each row has a separate thing, right? But then this was the actual profit. right? This one right here was the profit. And then these were the left-hand sides of the constraints, right? This one was the total carpentry time, and then the 100 was the total painting time. And the right-hand sides were just the limits, right? The carpentry time had to be less than 240, the painting time had to be less than 100. Okay, we're gonna do this in more detail in the next one. So let's just get to the next one, and then you'll see. Okay, so we're going to talk here about some of the different applications we're doing. We're going to be doing the chair and table example was a product mix example. It was a really simple product mix example, but that's just about, how many of each type of product should we produce to maximize our profit while meeting certain conditions, right? But there's other sorts of things to do with other problems. We can do marketing. So with marketing, this one is going to be about trying to decide what ads to buy, right? Do we want newspaper ads, online ads, TV ads? And we have two goals, right? We want to maximize our audience exposure and we want to minimize advertising costs. And so in each problem, we're going to be deciding essentially one of these will be the objective, right? Either we're going to have a budget and we're going to try to say maximize our audience exposure within that budget, or we might go the other way. We might say we have a certain amount of audience exposure we want, and we want to do that as cheaply as possible, right? So those will be two ways to go. We're either going to say we know in advance what the audience exposure should be, and we're going to minimize our costs, or we can say we know in advance what the costs are going to be, and we're going to maximize our audience exposure. Right, so in this example, it says we have this club, we're promoting trips to the Bahamas for gambling. We have $8,000 per week to spend on advertising, right? So we have a budget. And we want to maximize our possible audience. And there are different media types, which are shown on the next slide, that are going to tell us how many people we reach, how much does it cost, and so on. But we have two other constraints here before we go to the next slide, which is that we need to place at least 5 radio spots per week, and no more than $1,800 can be spent on radio advertising each week. Okay, so those are some limits we have on radio advertising. So if we look at the types of spots, types of ads we can get, it's TV spots, newspaper spots, and then 2 different lengths of radio spots. And we can see here that we have the audience exposure, right? We have audience exposure for the different types of ads. The newspaper has the largest exposure. The radio has the smallest exposure. But then there's also the price, right? The prices. Newspaper ads are the most expensive. Radio ads are the least expensive. And there's a maximum ads per week. So we can't buy more than 12 TV spots per week. We can't buy more than 5 newspaper ads per week. And so on. So these will be constraints. All right, when we make this problem, the first thing we want to figure out is what are our decision variables? What do we have to choose? And in this case, it's pretty easy to see that the decision variables are the 4 types of ads, right? How many of each type of ad are we going to buy? Or instead of how many of each type of ad are we going to buy, we could choose the decision variables to be how much money are we going to spend on each type of ad. And now both of these methods would work, right? If our X1 was the number of TV spots we buy, we could formulate the problem that way. If X1 was the total dollars spent on TV spots, we could formulate the problem that way. And both of them would work. But one of them is going to be easier than the other because of how all the information is given. Some of the constraints are going to be easier to write one way, some of them are going to be easier to write the other way. But if we look at the majority of the constraints, we have these maximum ads per week constraints. Those are 4 separate constraints. Those are going to be easier to write if we're writing them in terms of number of ads. Right? If we're doing X1 is the number of TV ads, then that constraint maximum ads per week is 12 for TV. That will just be X1 is less than or equal to 12. Right? It'll be really simple. If we wanted to make X1 instead represent the dollars spent on TV ads, then that constraint would be more tricky, right? We'd have to take the dollars spent and divide by $800 per ad to get the total number of TV ads bought. So it would look like X1 over 800 is less than or equal to 12. Right? So we can do that, and it does work, but it makes it a little bit trickier. The budget constraint, on the other hand, maybe is actually easier doing the other way, right? If X1 is the dollars spent on TV ads and X2 is the dollars spent on newspaper ads, then having a budget of 8,000, that would just mean that X1 plus X2 plus X3 plus X4 would be less than or equal to 8,000. So the budget constraint would be really easy in that case. If we do it in terms of number of ads, right? If X1 is the number of TV ads, then for the budget constraint, we have to multiply that by $800, right? How much money do we spend on TV ads? It's $800 times the number of TV ads. Okay, so those are going to be 2 different ways we can do it. And I'll show you that we're going to get the same thing. I will do both of them in Excel. Okay, so before we go to Excel, we want to make sure we know what we're talking about here. So the constraints are going to be about the maximum number of ads per week. There's 4 of those constraints. And then there's a budget constraint, cost per ad. We'll have to, go into calculating our budget constraint. And then we also have the 2 extra constraints here that we have to place at least 5 radio spots, but not spend more than 1,800 on radio spots. Okay, so those are going to be extra constraints. So we're going to have 7 constraints in total. The 4 maximum spot constraints, and then these 2 extra constraints, and then the budget constraint. So let me see here. What's the best way to do this? I want to be able to alt tab back and forth between them. So I think the best way to do this is just to share this screen. Okay. So this is going to be our advertising. So our variables are going to be the different types of spots, right? So we're going to have TV, newspaper, 30-second radio, and 60-second radio. Like I said, I'm going to do this both ways. The first way I'm going to do it is in terms of number of ads, right? So this represents the number of TV ads, the number of newspaper ads, and so on. Okay, so we're going to have our decision variables here. And then below that, we set up our objective. So the objective function here, we need the audience for each ad. So each TV spot reaches 5,000 newspaper is 8,500, and then 2,400, and then 2,800. So 5,000, 8,500, 2,400, and 2,800. These are going to be the coefficients. So if we bought, say, one TV ad, we would reach 1 times 5,000 people. If we bought 2 newspaper ads, we would reach 1 times 5,000 plus 2 times 8,500, and so on, right? So over here, the total number of people we reach is the sum product of these two rows. And I'm going to make the red one, the decision variables, static. Right? So if we bought 1 TV ad and 2 newspaper ads, we would reach 22,000 people. Okay, so that's my objective function set up here. And now my constraints. I have different constraints here. I have the constraints based on the budget. I have the maximum TV spots. I have the maximum newspaper spots. I have the maximum 30-second radio spots. I have the maximum 60-second radio spots. I have to get at least 5 radio spots overall. That radio spots, that would include both of these, right? These together have to be at least 5. And then I have my radio budget of 1,800, right? So these are my 7 different constraints that I'm going to have down here. So if we start with the budget constraint, right, the left-hand side has to be how much money did we spend? And that depends on these costs. 800, 925, 290, 380. 800, 925, 290, 380. Right, so if we take this sum product here and we copy it down there, and we just put some numbers in here, right, we can see how much we're paying. Right, this is the left-hand side of my constraint. This is the total amount spent. Right, if we buy 1 TV ad, 2 newspaper ads, 3 30-second radio ads, and 4 60-second radio ads, then we have spent 1 times 800 plus 2 times 925 plus 3 times 290 plus 4 times 380 is $5,040. And that needs to be less than or equal to 8,000. Okay, so this column G just has the symbols. It's not really necessary to have this column here at all. But it does serve as a little reminder when you're setting up solver, which ones are less than, which ones are greater than. So I like to have it. Okay, so that's how we set up the budget constraint. Now, the next one is the maximum number of TV ads. So the left-hand side is the number of TV ads, and the right-hand side is, if we look on the sheet, right here is 12, right? We can have the maximum TV ads should be 12. So we know this is going to be less than or equal to 12. And here we could just say this is the number of TV ads, just have a cell reference there. That needs to be less than 12. See, that works fine. But the other way to do this, because we could have, like, this is the number of TV ads, this one is the number of newspaper ads, this one is the number of radio ads, and so on. This one is the number of 60-second radio ads. We could do all these like this, but if we want to just use this same formula all the way down, which we should be able to do, then what we can do is, instead of doing a cell reference, we can just make this a 1. Right? Because now we get this cell is 1 times 1 plus 2 times 0 plus 3 times 0 plus 4 times 0. So we can just leave these blank. We can put zeros in, or we can leave them blank. Either one's fine, right? But now by having a 1 here, we're referring to 1 times the number of TV ads. And then for newspaper, we put a 1 there, right? 1 times the number of newspaper ads. And for 30-second radio slots, we put a 1 here. And for 60-second radio slots, we put a 1 here, right? So we can see that what we get here is the number of TV ads, the number of newspaper ads, and so on. So
Professor, I'm slightly confused. Where did you get the 12 from?
the 12, that's from the restriction here. The maximum number of TV spots is 12. Right? So this number needs to be less than 12. The total number of TV spots, right, which is 1 times this number here, needs to be less than or equal to 12. And then we have restrictions on newspaper slots and radio spots and so on as well, right? So 5, 25, and 20. Right? Those are our constraints from the slides. Right? So if we're buying ads like this, right, then all of these constraints are met, right? We haven't exceeded the maximum number of ads of any type if we do this. So this is fine, right? This is right now, this is a feasible solution, right? It's not the optimal solution, but this is so far, at least, this is feasible. So the next constraint is that we want at least 5 radio ads. So here we want the total number of radio ads. So we really want like this plus that to be at least, so greater than or equal to 5. Right? It should look like 7 is greater than or equal to 5 right now, because we're buying 3 and then 4. So this is fine, except that if we wanted to use the same formula, we wouldn't do it this way, right? If we wanted to use this formula, what we would do is we would put a 1 here and a 1 there. Right? We're adding up 1 times the 30-second radio ads plus 1 times the 60-second radio ads. And that gets us the total number of radio ads. 7. Right? So by putting a 1, we're just saying we're counting that variable by itself, right? The 30-second radio ads variable plus the 60-second radio ads variable. That's what those 1s are doing. And like I said, we can put zeros here or we can leave them blank. It's fine either way. And then finally, we have our radio budget. Right? The radio budget, it said no more than 1,800 can be spent on radio ads. So whatever we get here has to be less than or equal to 1,800. Now, the radio budget involves these prices again, right? The same prices, the same costs, but only for the radio variables, right? Because this is the radio budget. We don't care about how much we're spending on TV or newspapers. We want to do the 290 here and the 380 there. Right? So 290 times the number of 30-second radio ads plus 380 times the number of 60-second radio ads, that will get us the total amount that we spend on radio. Okay, so this is now everything is set up. And we can see that this last constraint means that this solution that we picked is not actually a feasible solution, because this number is not less than 1,800. Right? So by doing this, we have spent more than our radio budget. So that's no good. That's not allowed. Okay, so with this setup, we have all our 7 constraints. We have our objective function. Everything's using nice formulas. So we're going to be able to use solver now. So if we go data, solver, the objective is here, right? This is the total audience reached. We're trying to maximize that by changing the variable cells here. Right? This is up here, this is the objective. We're going to maximize the total audience reached by changing these variable cells. Now it says I want to add the constraints. So I click add. And like I said, you can do these in batches. You can do all the less thans. Now, unfortunately, it doesn't let you put in commas like this. If I do this is less than or equal to that, just trying to select all the lessons at once, I don't think it likes that. It says cell reference box is empty or contents are not valid, right? It's not valid. So what I usually do is I just sort these so that all my less thans are in a group, but you can also just split it up, right? So these less thans here, we're doing the first group of less thans. The first 5 are all less than, right? F5 to F9, these are all less than. So I'm going to add that constraint. Next, this constraint is a greater than or equal to. I'm going to add that. And then finally, this constraint is another less than or equal to. I don't need to click add because I can just click OK, right? When you're at your last constraint, you can just click OK, and that'll add it as well. So you can see I've got the first 5, right, on rows 5, 6, 7, 8, 9. Then I got row 10 and I got row 11. I have all my constraints here. This needs to be checked off because I'm not allowed to buy negative ads, right? I can't pay negative money to get a negative TV ad. That doesn't make any sense. So everything needs to be non-negative. And this is going to be simplex LP. Okay, so this is what solver's setup has to look like. And when we click solve, it gets us a solution. Right? Now these are not integers, that's okay, right? If this is 6.2, what does that mean? That means that most weeks we'll buy 6 spots, but some weeks we'll buy, like 1 in every 5 weeks, we'll buy a 7th spot. Right? So then we get like an average of 6.2 spots per week. Right? This is 1.968, right? That means we're buying 2 spots almost all the time. Occasionally we might buy 1 spot just to get the average to work, but that's what this does. If you want to force these to be integers, Excel can actually do that, right? You don't have to worry about like rounding it by hand and trial and erroring it. Excel can actually just do this for you. If we add in a new constraint that says these values have to be integers, and now I click solve, now it gives me the integer solution. Okay. So this is good if you need them to be integers. It does limit you in some ways because some of the follow-up stuff that we're going to do now is not available when you force things to be integers. So I'm going to talk about the follow-up stuff now, right? If I click solve here with this integer thing, you can see the only report available is answer. That's the only report available. But if I go back into solver and I get rid of that constraint, I delete the one that says they have to be integers. I don't want that. And now I click solve. You can see there's more. There's the answer and the sensitivity. Also limits. Not going to know what limits. Today I just want to talk about the answer report and the sensitivity report. So I highlight those two and then I click OK. And then it gives me new sheets. It gives me the answer report and the sensitivity report. So the answer report, we can see what are the values that we get, right, for our decision variables. 1.96875 TV spots, 5 newspaper spots, 6.20689 30-second radio spots, and 0 60-second radio spots. Those are how many ads of each type we should buy. The final value of the objective function is 67,240.3. That's how many people are seeing our ads. That's the total exposure. Right? And then down here, we can see for all the constraints, which ones were binding. Now, a binding constraint is one that where we've met the amount exactly, right? There were a maximum number of 5 newspaper ads, and we are buying 5 newspaper ads. So we can't increase the number of newspaper ads. That's binding, that's restricting us. Right? We can't go higher. We are not at the maximum for the others, right? We're buying 6.2 30-second radio ads, but we could have bought, if we look back at the restriction, right? We were buying 6.2 of them. We could have bought 25 of them, and it would have been fine, according to this constraint. So that constraint's not binding, right? You can see the ones that are binding are the ones where the left-hand side equals the right-hand side. So the 5 equals the 5, the 8,000 equals the 8,000, the 1,800 equals the 1,800. Those are the ones that are listed as binding here, right? The 1,800 radio budget, the 8,000 budget, and the 5 newspaper ads. Everything else is not binding. Not binding constraints have slack, right? The slack is how much could you change the left-hand side of this constraint and still meet the constraint, right? So we're buying 6.2 radio ads, but we could have gone up to 25. So 25 minus 6.2 is the slack, the 18.8, right? We could have bought 18.8 more 30-second radio ads. That's what the slack means. That's how much of the resource is left over, unused, right? So the available radio ad spots that we could have bought, but we didn't, 18.8 of those. Okay, so our budget is binding. We have no slack. In other words, we have no money left over. If there was slack in the budget, that would mean we had extra dollars that were unspent. Visually, if you're doing this in 2 dimensions with a graph, a binding constraint is one of the lines that touches the optimal point. Right, so this is non-binding. I want you to make sure that you understand the difference between non-binding and redundant. A redundant constraint, like we talked about last week, doesn't even touch the feasible region. You could remove it from the problem and the feasible region would not change. A non-binding constraint can still touch the feasible region, it just doesn't touch the optimal point. Right? There's one corner of the feasible region that is the optimal point. A non-binding constraint won't touch that corner, but it might still touch the feasible region. Right? So redundant constraints are always non-binding, but non-binding constraints don't have to be redundant. Okay, so now we have the sensitivity report. In the sensitivity report, I want to talk to you about 2 things. I want to talk to you about up here, this area here. This area here is going to give us what we call our range of optimality. So what this does is this says if the objective function coefficients start changing on us, that will change essentially the slope of the objective. And if that slope changes just a little bit, then we're not going to change our optimal decision. Our optimal decision is going to stay the same. But if that slope changes enough, then we will change our optimal decision. Okay, so how does this work? We have these objective function coefficients right now. This is the audience levels, right? 5,000 people will see each TV ad, 8,500 will see each newspaper ad, and so on and so on. That's the coefficients. Now, what happens if the TV ads start to become more or less effective, right? If that 5,000 number starts to go up or down. If it goes up just a little bit, if it goes up from 5,000 to say 5,100, that's not actually going to change our optimal solution. Our optimal solution is still going to be to buy whatever it was, 1.97 TV ads, 5 newspaper ads, and 6.2 radio ads. Right? That's still going to be the optimal solution if it goes up by 100. But eventually, if it goes up by enough, all of a sudden something will shift, right? And the allowable increase is here, right? So this tells us that if this 5,000 increases by this much, right? So we can see what is 5,000 plus that, right? This is our critical tipping point here, right? As soon as the number of people a TV ad reaches goes above this level, TV ads become more efficient than whatever we were buying before, right? Currently, we're not buying TV ads as many as we could, right? We're not limited in our TV ads. The number of TV ads was not binding. We could buy more TV ads, but we're not because the other ads we're buying are more efficient, right? They give us more audience per dollar. But if the TV ads if the audience grew to above this number, all of a sudden the TV ads would be more efficient than whatever we're buying now. And we would start shifting our investment into those. So we would start maybe buying less radio ads and more TV ads, or maybe it would be less newspaper ads and more TV ads, or something, right? This is sort of the critical point where we would start buying more TV ads if the TV ads audience level went above that number. Right? So if the TV ads audience number went up to 6,600, that wouldn't be big enough. We still would not change our decision. But if they get to 6,700, now that's bigger. Now we would change our decision. Okay, so this tells us essentially a limit, an upper bound. And we have a lower bound as well. What's the lower bound? That's based on the allowable decrease, which is going to be 5,000 minus 5,000. So 0. Now this might seem weird. You're like, wait a minute, really? If we have to go all the way down to 0 before we stop buying TV ads? That seems crazy, but it's actually correct. So I want you to imagine, what if this 5,000 dropped all the way down to 1? What if only one person was watching TV? And so our audience number was 1 person for each ad we buy. We would still buy TV ads. Why is that? Why is that? So let's go over and see. We have $8,000 to spend, right? And we're already maxed out on newspaper ads. We bought 5, and the maximum newspaper ads we can buy is 5. We're also maxed out on radio ads, not because of these constraints, not because of these constraints, but because of the radio budget. We're spending our entire radio budget. So even if TV ads were terrible and only reached a single person, after we buy 5 newspaper ads and spend our entire radio budget as efficiently as possible, and currently that means buying 30-second radio spots and not 60-second radio spots, because the 30-second radio spots are more efficient than the 60-second ones, we would still have money left over. And as long as that money could get us even 1 audience member, we would spend it, according to this problem, right? And so even if we're getting only 1 audience member per TV spot, we'll still buy them because we got money to spend, right? We have money left over in our budget. So we can see if we change this to a 1, and we rerun solver, these numbers won't change. Right? If I go to solver, rerun this, nothing changes. We're still spending this money on TV ads because if we didn't, our audience would go down. Not by much, right? Not by much at all. but the audience will go down, and so the problem is trying to maximize that. So even if the audience was only 1, we would still go for that. We would still buy TV ads. Okay, so that's what this is telling us. We're not going to stop buying TV ads until the audience level goes down to 0. Right? So we can do similar things here with newspaper ads, right? Right now we're buying 5 newspaper ads. What's the lower bound? The lower bound is the 8,500 minus the allowable decrease. So as soon as the audience level for newspaper ads goes down below this value, below 57.81, then we'll start shifting our money away from newspaper ads. Right now we're buying 5 newspaper ads because that's the maximum number of newspaper ads we can buy, because newspaper ads are the most efficient thing we can do right now. But if the audience level went down for newspaper ads and they stopped being the most efficient, we would stop buying them. We would buy different things instead. We would shift our investment from newspaper over to TV or whatever. What's the upper bound? Well, it's infinity. There is no upper bound. Why is that? Well, because in this problem, right, if the amount of people the newspaper ads reach increases, would we buy more newspaper ads? No, we can't, because we're already maxed out. We're already buying the maximum number of newspaper ads. There's a constraint, right? 5 newspaper ads is the constraint. We can't buy more. So it doesn't matter how efficient they get. If they get more efficient, we're limited, right? If newspaper ads got even more efficient and reached even more people, we couldn't buy more. Right? We just can't, right? So we can say same thing for all of these, right? For the 30-second radio ads, it doesn't matter if they get less efficient. If the audience level goes down, then we'll stop buying them. We'll start shifting our investment from 30-second spots to 60-second spots if the 30-second spots gets less efficient. But if they go up, we're stuck. We can't invest more in 30-second radio ads because we're already hitting our radio budget, our $1,800 radio budget. And then here, for 60-second radio ads, it's the same idea. If they get less efficient, this is negative infinity here, right? Negative 1 EU plus 30, right? That's negative 10 to the 30. This is like negative infinity. So if they get less efficient, it doesn't matter. It doesn't matter if they reach fewer people. We can't reduce the number we're buying because we're already buying 0. We're not buying any. They already suck, all right? The 60-second radio ads are bad. They're not reaching enough people. We're not buying them. If they started reaching less people, we would still not buy them. On the other hand, if they started reaching more people, if they started reaching 3,145 people, for instance, now they would be more efficient than the 30-second radio ads, and we would shift our investment from 30-second spots to 60-second spots. Okay, so having these lower bounds and upper bounds set up allow us to know when do we have to change our tactics, right? So we know what our current investment is. We know how many ads we're buying now, but these serve as sort of triggers, right? If one of these numbers goes outside these bounds, we're going to redo this. We're going to recalculate, come up with a new strategy for the new situation. Okay, and the other thing to know is these are only about what if one of these happens by itself, right? So if this number changes and all the other numbers stay the same, what happens? This stuff does not take into account what if multiple ones of these are changing at the same time. What if this 5,000 goes up by a bit and the 8,500 goes down by a bit? This doesn't take that into account, right? This is only about what if one of these changes at a time. Okay, so this is called the range of optimality. Okay, so each coefficient has a range of optimality. The other thing we want to talk about is the shadow price. which is here. So what the shadow price says is what happens if we change the constraint a bit, right? Now, if we change the right-hand side of a constraint. Now, you'll notice that a bunch of these are zeros. Those are the non-binding constraints. If you change the right-hand side of a non-binding constraint by a little bit, nothing happens. Right? If we look at this, say the maximum 30-second radio spots constraint, if we look at that one, right? The maximum 30-second radio spots was 25. If that 25 goes up or down by a little bit, if it goes up to 26 or down to 24, what happens to our solution? Nothing. Right? We're not binding, right? We're not at the maximum. So if that 25 changes to a 26, we don't care. We're not going to buy more. Right? We're already limited by the radio budget. Right? But this one, the newspaper ads, that one is binding. Right? So if that 5 goes up to a 6, if we can buy more newspaper ads, we can reach more people. And we will do that. Right? So if this 5 goes up to a 6, and if we're allowed to buy an extra newspaper ad, then we'll start shifting our investment away from TV ads and into newspaper ads. That's what we will do. So if that 5 goes up to a 6, then our solution is going to change. And so what this shadow price tells us for here, that's this number here, right? This tells us that if that 5 went up by a single unit, if that 5 increased to a 6, then we would be able to reach 2,718.75 additional audience members, right? This is how much our total audience would change for each additional newspaper ad we could buy. Right? So if the 5 goes up to a 6, then we will be able to reach, we'll buy more newspaper ads and we'll be able to reach some extra people. If the 5 goes down to a 4, then this number is how much our audience will drop. If the 5 goes down to a 4, we won't be allowed to buy as many newspaper ads. We will shift the investment away from newspaper ads and into TV ads, and that will reduce our overall audience. Because the limitations just got stricter, right? That's what the shadow price is all about. This number here is about the budget, right? That's also binding. What does this tell us? This tells us that currently our budget is $8,000. But for every dollar we increase our budget, we can reach 6.25 additional people. Right? So if we increased our advertising budget by $100, if that 8,000 went up to 8,100, we could reach an additional 100 times 6.25, so an additional 625 people. Right? So this tells us the result of increasing our budget. At least by a small amount. If you increase your budget a ton, then things can shift more. If you imagine the pictures, like with the lines on the graph, and imagine one of those lines shifting a bit. If it shifts a bit, then the optimal point moves along with it. But if it shifts too much, then it can become redundant, or the optimal point can get stuck on a different constraint or something. So the shadow price is not true forever. Right? The shadow price is not true forever. We can't, it's only applicable within a certain range. And that's what this allowable increase and decrease stuff is about, which I'm not going to go into detail on. But this sort of tells us where where things can shift, where that right-hand side of the constraint can shift, and still give us the same solution. And where the shadow price makes sense. So these are the shadow prices. Non-binding constraints don't have a shadow price. Binding constraints have a shadow price, right? If we increase our radio budget, then we will reach more people because we can shift money from TV ads into 30-second radio ads, which are more efficient. Right? So by increasing our radio budget, we'll reach more people. By increasing our, even if we don't increase the budget, even if we keep the budget at 8,000, if we allow ourselves to spend more of that on radio, we'll get better results. Right? And this tells us how much better. Okay, so that's shadow price. Shadow price is if you increase the right-hand side of a constraint by 1 unit, how much increase or decrease, sometimes it could potentially be a decrease, will the objective function see? Right, like sometimes it's a decrease because sometimes your objective function is something you're minimizing, right? Sometimes it's like your costs. So by allowing you to invest more in one area rather than another, you may be able to reduce your costs. So the shadow price could be a negative number there. Right, whereas the range of optimality is about how far can the objective function coefficients change before we change our optimal decision. Okay, so that's shadow price and range of optimality. Those are the sort of what if things you need to know about. And in your assignment number 4, it has a couple of questions on these. It'll have one objective function coefficient question, right? One range of optimality question, and it has one shadow price question. Okay, so I also promised I would show you what happens if we did the advertising with different units. So I'm going to show you that. I'm going to go pretty quick because I want to have time for the other stuff. But what if this is not number of ads? What if this is dollars spent on ads instead of number of ads? Right, so now we have still these 4 are going to be the variables, but now the objective function is just going to be 1 times each of these. Right, because now these are in dollars. This makes the budget constraints easier, right? Because now, oh, sorry, not the objective. Sorry, that's not the objective. That's the budget. The budget is all ones because now these are in dollars, right? And the radio budget is just ones because now these are in dollars, right? 1 times the dollar spent on 30-second radio plus 1 times the dollar spent on 60-second radios gets us our radio budget. But these ones all get trickier to write, right? The maximum amount we can spend on TV, right? We can only have 12 TV ads. So this has to be the number of TV ads divided by the price per TV ad, right? 800, right? So this is 1 over 800. Right? So if we spent $800 on TV ads, look, right? If we spent $800 on TV ads, 800 times 1 over 800 is 1, right? This is the number of ads. If we buy 2 ads, then we've spent $1,600, right? So that becomes a 2, right? So the dollars goes here, and then the number of ads will show up here. He's doing 1 over 800. And then here for newspaper ads, I have to do 1 over 925. And then here we're doing 290 and then 380, right? 1 over 290, 1 over 380. And then here for at least 5 radio ads, we need to do the 1 over 290 and the 1 over 380. So now, and then the objective function is actually even more annoying because that's the audience reached. we have the audience reach per ad, but we want the audience reach per dollar. So this has to be not 5,000, but 5,000 over 800. And this has to be 8,500 over 925. And this one has to be 2,400 over 290. Right? Because we're doing audience reach per dollar. And this is 2,800 over 380. Right? And if we solve this, right, if we go into solver, we're going to set the objective here. We're going to maximize that by changing these variable cells. We got to get rid of these constraints and add in a whole new set of constraints. Right, so these numbers have to be less than or equal to these numbers. And this has to be greater than or equal to this. And this has to be less than or equal to that. Solve it. What do you see? The result is the same, right? This number is the same as this number. We get the same audience. We're actually making the same decision, right? It's just up here, it's not telling us the number of ads, it's telling us the amount of money we're spending, right? So instead of saying we're buying 5 newspaper ads, it says we're spending $46.25 on newspaper ads. But that's the same thing, right? 5 ads at $925 per ad gets us $46.25. Right? So you can solve the problem using these units. In this particular example, doing number of ads makes more sense than doing dollars spent on ads. All right, but that's just this particular example. There may be other examples where doing your units in terms of dollars is going to make more sense. Depending on what your objective is, depending on what your constraints are, that could be the way to go. Okay, so now let's get into some of these other ones. With these other problems, I'm not going to focus on the solving of them. I'm just going to focus on the formulation of them.
Last time, and I think many students did only 2 questions, and one is optional.
Oh, sorry, I didn't hear the start of your question. Can you start again? Okay, maybe.
Sorry, that was my mistake. I'm sorry.
Oh, okay, no problem. That's all right. Yeah, okay. Yeah, so we're gonna go on here and look at some of these other applications. So like I said, we're going to focus on the formulation, right? Because the solving Excel handles, right? Once you've got it formulated and in the correct format, Excel can handle that. So with this problem, this is an investing problem. ICT has $5 million to invest, and it wants to accomplish 2 things. It wants to maximize the return on investment over the next 6 months, and it wants to satisfy the diversification requirements set by the board. The board has also decided that 55%, at least 55% of the funds must be invested in gold stocks and construction loans, and no less than 15% to be invested in trade credit. Right, so at least 55%, that's greater than or equal to 55%, and no less than 15%, that's also greater than or equal to. Right, so these are actually both greater than or equal to, they're just using different words. Right, watch out, if you're not being careful, it's very easy to make a mistake. I feel like I might have actually made that mistake on Tuesday. I might have thought that was no more than 15% when it's actually no less than 15%. So I might have messed that up on Tuesday. Anyway, the wording can be confusing if you're not paying attention. We also have this slide which shows us the interest, right? So we're trying to maximize the total interest, right? So 7% of whatever we invest in trade credit, 11% of whatever we invest in corporate bonds, 19% of whatever we invest in gold stocks, 15% of whatever we invest in construction loans. Right, so the variables in this case are easy. We're going to see some questions in a minute where the decision variables are tricky. But in this case, the decision variables are easy enough. It's just, what are we investing in? It's just the four things. But what are the units, right? So, right, we have trade credit, corporate bonds, gold stocks, construction loans. Those are the four decision variables. That's what we control. But the units in this case are dollars. The units have to be in dollars. You could write a different version of this question where it talked about what was the price per share of each of these stocks. And then you'd have a choice between writing out your variables in terms of number of shares versus writing out your variables in terms of dollars. But in this case, they don't actually tell you, right, anything about the number of shares. Everything is in terms of dollars, right? The interest, that's 7% of the dollars you invest, right? The amount of interest you make is 7% of the money you invest. The maximum investment in millions of dollars, right? Over here, right? 55%, right? So of the funds, if the funds are in dollars, then 55% of the funds is also in dollars, right? So we know that we're writing these variables in either dollars or thousands of dollars or millions of dollars, right? You're allowed to choose that, right? That's not going to make much difference. If I write 5.5 instead of, 5,500,000, that's fine, right? As long as you're just clear about what you're doing, right? So when I'm doing this, I might want to write my decision variables in terms of millions of dollars, right? Or I might write them in terms of dollars, right? In this example, right, as decision variables, that's in dollars. And that's fine, right? You can write it in dollars, you can write it in millions of dollars. It won't be easier or harder. It'll be the same. Okay, so this is our objective now. The objective is to maximize the return. And we do that by writing it out like this: 0.07 times the amount of money you invest in trade credit, right? 7% of whatever you invest comes back as interest. 11% of whatever you invest in corporate bonds comes back as interest. 19% of whatever you invest in gold stocks comes back as interest. 15% of whatever you invest in construction loans comes back as interest. So the units here on this objective function are going to be the same as the units for our decision variables. If our decision variables are in dollars, then the return here is going to be in dollars. If the decision variables were in millions of dollars, then the return here is going to be in millions of dollars. Right? This will be written the same way regardless of what the units are for x1, x2, x3, x4. All right, that's maximizing the return. Okay, so if we wanted to put this on our Excel sheet, we would just put in these coefficients, the 0.07, the 0.11, and so on, right? Those would go in the Excel sheet. I don't think I'm necessarily going to do this one in Excel, but just because you've already seen it, right? It's just about what are the coefficients. Okay, so let's go on to the constraints now. These maximums are easy, right? The total amount of money invested in X1 has to be less than or equal to $1 million. That's what it says, right? This is easy. X1 is less than or equal to 1 million. X2 is less than or equal to 2.5 million, and so on, right? All of these maximums just come from here. These are easy constraints to write. We also have the maximum total investment. That's our budget, right? You have $5 million to invest. We can't invest more than that, right? So the total amount invested, x1 plus x2 plus x3 plus x4, is less than or equal to 5 million. These constraints do depend on the units, right? So if x1 and x2 are in dollars, this is what we do. If they were in millions of dollars, then we wouldn't have a 5 million here, we would have a 5. Right? If we were doing millions of dollars, this would just look like that. Right? And these ones, instead of being 1,800,000, would just be like 1.8. Right? If they were in millions of dollars, that's what we would have. Right? But it's not like it's harder or easier one way rather than the other. It's fine whichever way you do it. So these constraints are easy. Where things get a little bit trickier is the other constraints. Now, what's happening here? There we go. So these text boxes are sized slightly wrong. Okay. All right. So at least 55% of the funds must be invested in gold stocks and construction loans. Now, there's actually two ways to think about this, and you have to be clear on what you're doing. When it says the funds, does that mean the $5 million that you have available to invest? Or does that mean whatever amount actually gets invested? Now, in all likelihood, it's not going to matter. Because in all likelihood, what's going to happen is we're going to invest all $5 million, right? So if we invest all $5 million, then it doesn't matter what we mean, because we're going to get the same answer anyway. But the $5 million is only a maximum, right? We don't actually have to invest all 5 million. It's possible that we only invest 4 million or 3 million or something, right? So if we only invested 4 million, then we would want to know, what does this restriction mean? If we only invest 4 million, then is this at least 55% of the 5 million we had available? Or is it at least 55% of the 4 million we actually invested? If this is at least 55% of the available funds, then it's actually going to be pretty easy. It's not going to look like this example down here. It's actually just going to be like, let me do it here. 55% of the 5 million. Right? X3 plus X4, that's the gold stocks and construction loans. Right? That was X3 and X4. Has to be at least 55% of the funds available. But if the funds means the funds actually invested, then the funds actually invested is this total, x1 plus x2 plus x3 plus x4, and that makes our constraint look like this. Right? So depending on which way we interpret this phrase, the funds, we could write this constraint this way, or we could write it that way. Right? This says the x3 plus x4, the total in gold and construction loans, has to be at least 55% of the total funds invested, x1 plus up to x4. Okay, now if we write it this way, we have to do some rearranging, right? We're not allowed to put it into Excel like this, right? When we put it in Excel, we need to have all the coefficients and everything on the left and only have a constant on the right. So we have to expand out these brackets and then move everything over to the left. And when we do that, we get this, right? So this one is just a rewriting of this one. Oops. Right? So these bolder ones are the same constraint, just rewritten. This is the way we need it to go in Excel, right? We need the negative 0.55 for the first slot, the negative 0.55 for the second slot, the positive 0.45 for the third slot, and the positive 0.45 for the fourth slot. That's 4. Right? And then we have the exact same thing with the trade credit. No less than 15%, right? Is that 15% of the funds available? Right? Are we doing X1 is greater than or equal to 0.15 times the 5 million? We might be, right? We might be doing that. There we go. Right? So we could write our equations like these, or we can write them like these ones over here. Right? This would be our final two constraints. If we, depending on exactly what we mean by the question. Okay, so if we end up spending all $5 million, then it doesn't actually matter, right? Then these will actually be totally equivalent. These will be exactly the same if we spend all $5 million. But if there's some constraint that prevents us from spending all 5 million, if there's some reason we can't invest all 5 million, then it does matter which one of these we pick, right? And we'll have to figure out, based on our real world situation, which one of these is meant. Right? If this is supposed to be for diversifying our portfolio, if we only invest 55% of the funds available, then does it make sense that we can put them all into gold and construction loans? And then say that that's good, or what, right? Like, how does this work? If we decide that we're investing less, what are our actual requirements? Right? So I can't tell you based on this sentence alone which one is the correct answer. Right? You would have to understand, what does the board want you to do in the scenario where you actually end up investing less than 5 million. Okay, so we have these two different ways of writing the constraints depending on what the board means. Right? And of course we have non-negativity as well, but Excel handles that automatically with that checkbox. Right? And like I said, I'm not doing this one in Excel in the interest of time. We've already done some Excel stuff. But if you did it in Excel, you would get this solution. Okay, so like I said, in the interest of time, we're moving on. We're going to do a transport problem. In these transport problems, we have the distribution of goods from supply points to demand points. We have sources and destinations. Sorry, I just got a text from my daughter. She needs me to bring something to her. You know what? Now's a reasonable time for a break anyway. We've been going for a while, but I need to know, do you have anything on later? Because like we started late already. So I'm wondering if we took a break now and came back, do you have other classes and stuff that you need to do? Because we probably got about half an hour more to teach. So if we take a 10-minute break and then another half hour after that, is that all right? You don't have other places you need to be?
Our second class is also online, so it's okay, I guess.
But what time is it? What time is the second class?
1:30.
Okay, so you're fine then. Yeah, it's not a problem. Okay. Great. So I'll take a 10-minute break, maybe 15. I'll have it just drive over to my daughter's camp and then drop something off for her. And then yeah, I'll be back in 10 or 15 and we can continue this. All right, so let's continue. We're going to do these transportation applications now. So with these transportation problems, we want to minimize total costs. And these could include transportation and production costs. In the example we're going to do, we're only going to have transportation costs. But you could also have production costs in here if the different sources had different production costs. We're going to have constraints based on the capacity of goods at each source and the requirements at each destination. And so we're going to see that on the next slide. So we have 3 different sources, A, B, C, Albuquerque, Boston, Cleveland, and 3 different destinations, D, E, F, Des Moines, Evansville, and Fort Lauderdale. And we have different prices that it takes to ship from each source to each destination. And so this is an example where if you try to come up with the decision variables, it's not necessarily obvious what they should be. Right? You're trying to think, like, what things do I control? I control what can I decide? I can control how many products are coming from each source. Right, okay, but I can also control how many products are going to each destination. Right, so some of the students will say, oh, I have 3 decision variables, and then some of the students will say, no, I have 6 decision variables. Right, I have each source and I have each destination. But that's still not correct. There are actually 9 decision variables because you control not only where do the products start, but where does each product go? You control the combination, right? So a product that starts in Albuquerque and goes to Des Moines has a different price than a product that starts in Boston and goes to Des Moines, or a product that starts in Albuquerque and goes to Evansville, right? So you have these different combinations, and the combinations are what's important for the shipping costs here, right? So you have 9 different combinations, and you can see those 9 here in the table, right? So when we make our variables, we're going to have 9 variables. Right? So we call them xij, right? So x11 goes from Des Moines to Albuquerque, x12 goes from Des Moines to Boston, x13 goes from Des Moines to Cleveland, or sorry, Albuquerque to Des Moines, Boston to Des Moines, and Cleveland to Des Moines, right? Or you know, X23 would go from Cleveland to Evansville, or whatever, right? Sorry, these are the sources. I had them flipped in my mind. The DEF are the sources, the ABC are the destinations. So yeah, it's from Des Moines to Boston, from Evansville to Cleveland. Right? So we can label our decision variables like X11, X13, and so on. Right? But they represent all the different combinations. So when we get our total cost function that we're trying to minimize, it looks like this, right? It's got the 9 different variables and all 9 of the coefficients from this cost table. Right? $5 to go from Des Moines to Albuquerque. $8 to go from Evansville to Albuquerque. $7 to go from Fort Lauderdale to Boston. That's here. Right? From Fort Lauderdale to Boston, from 3 to 2. Right? These are our 9 different things, right? Once you know that there's 9 different decision variables, the rest of this problem is not too difficult. The constraints are pretty easy. Right? But it's just a matter of making sure you understand that there are 9 decision variables and what they represent, and then the rest is not going to be hard. Right? For our constraints, we have the supply constraints. Each source can only produce a certain amount of goods. Right? They can only produce 100 goods in Des Moines, 300 in Evansville, and 300 in Fort Lauderdale. So we write out our constraints like this, right? X11, X12, and X13, all of those have 1 as the source. They all have different destinations, but they all have Des Moines as the source. So if we add up all of these, we get the total amount of goods that are coming from Des Moines. And that has to be less than or equal to 100. If we add up all the ones that have a 2 at the start, that's all the ones that are coming from Evansville, right? And we can't have more than 300 of those because that's Evansville's supply. Evansville cannot supply more than that, and so on. Right? So these are all less than or equal to's. Supply constraints are always going to be less than or equal to. These are capacities. Demand constraints, on the other hand, are different. Usually, we'll write these as equal to. So the demand constraints are here, right? X11, X21, and X31. So this is all the things that are going to Albuquerque. They all have a destination of 1. Right? They all have different sources, Des Moines, Evansville, Fort Lauderdale, but they all end up in Albuquerque. And the number Albuquerque demands is 300. Usually we write those as equal signs, right? Usually we don't want to send more than is demanded because then that's just a waste. And those products end up just sitting on the shelves or whatever. And we don't want to send less because we want to meet the demand, right? In certain situations, you may want to write this as a greater than or equal to, or you may want to write this as a less than or equal to, but usually we write these as equal to's, right? That's the default thing we do for demand, right? If the situation requires, then you can do differently, right? If the situation requires that sometimes we overfill demand or sometimes we underfill demand, then okay, right? But having these be like less than or equal to tends to create a problem where if these were less than or equal to, if we didn't have to fill the demand, then what's the computer going to think we should do? It's going to think we should do 0 goods from anywhere to anywhere, right? It's trying to minimize the costs. So if we don't have to ship anything, the minimum cost is if we just don't ship anything, right? So if we make these less than or equal to's, then the solution is just going to be 0, 0, 0, 0, 0, right? We ship nothing from anywhere to anywhere. So obviously that's a problem, right? So making these less than or equal to's is going to tend to have that problem if we're trying to minimize costs, right? Making them greater than or equal to's, okay, then we can. But if we do, probably what's going to happen is we're going to end up only meeting demand, right? Because if you try to, why would we ship more than demanded? It's just going to cost more. We're trying to minimize those costs, you know? So that's why generally having them as equal signs makes the most sense. Okay, so. And there's non-negativity. Right, so in this case, if we were to set this up in Excel, we would just set it up all in one big row. Now, I'm not going to call these X11 and so on. I'm just going to call these A, B, C, and D. So AD, AE, AF, and BD, BE, BF, CD, CE, and CF. So if we go to my prices here, right? We have 5, 8, 9, and we have 4, 4, 7, and we have going to Cleveland, we have 3, 3, and 5. And so this is going to be, oops, I need to leave a blank row, right? This is here, this is my objective. But I need to leave these cells blank for my decision variables. All right, so we have here the sum product of these and these. Make that static, right? This is my objective. This is my cost. I'm trying to minimize that. All right, and then for constraints, I have my supply and Des Moines. I have my supply in Evansville. I have my supply in Fort Lauderdale. I have my demand in Albuquerque. I have my demand in Boston, and I have my demand in Cleveland. Right, so for the supply in Des Moines, I'm just adding up all the things that are coming from Des Moines. And that has to be less than or equal to 100. And then for Evansville, I'm just adding up all the things that are coming from Evansville. And that has to be also less than or equal to, and now 300. And then Fort Lauderdale, I'm just adding up all the things that come from Fort Lauderdale. And that has to be less than or equal to 300. And then the demand ones are equal signs. Right, the demand ones were 300, 200, 200. So for Albuquerque, all of these ones are going to Albuquerque. None of these are going to Albuquerque, right? So that has to be equal to 300. And then all the ones that are going to Boston, that's BD, BE, BF. And then all the ones that are going to Cleveland, looks like this. Right? So if I have these, right, I'm adding up everything going to Des Moines. I'm adding up everything going to Albuquerque, sorry, coming from Des Moines, adding up everything going to Albuquerque, and so on, right? These are just all the different combinations. And I can set this up in Solver now. Right, my objective is here. I'm minimizing it. The variables I'm changing are here. The constraints are that all of these have to be less than or equal to all of these. Add that. And then all of these have to be equal to all of these. Right, and then I set this to simplex LP, and I can click solve, and I get a solution. If I want reports, I can get the reports. Right, I can start looking at which ones are binding. Everything's binding. Which one is what are the shadow prices? What are the ranges of optimality? I could look at all those things if I wanted to. All right, but I've got my solution here. 100 products are going from Des Moines to Albuquerque. 200 products are going from Fort Lauderdale to Albuquerque. right? That satisfies the 300 demand at Albuquerque, right? And then in Evansville, all the products to Evansville are coming from, so all the products going to Boston are coming from Evansville. And then all the products going to Cleveland, 100 of them are from Evansville and 100 from Fort Lauderdale. Right, so this gives me all the different combinations I need to know how many products to ship from each source to each destination. Right, all of these are binding because the total supply I have, 700, was equal to the total demand. If some of these had a larger capacity, right, if say Des Moines had a larger supply, then not all of them would have been binding, right? We would have had extra supply somewhere. But in this case, they're all binding. And we can look at things like, if we wanted to increase our supply somewhere, where would it make the most sense to do that? So if we look down here at all the supply constraints, which one has the best shadow price? The answer is Des Moines, right? If we increase our supply, if we increase our capacity at Fort Lauderdale, that doesn't help us. The shadow price is 0. We actually don't get any better results by increasing the capacity at Fort Lauderdale. If we increase the capacity at Evansville, we start saving money, right? We save $2 for each additional unit of capacity we have at Evansville. But at Des Moines, we save $4 for each additional unit of capacity. Right? So if we wanted to expand one of our sources, this shadow price tells us that Des Moines would be the best prospect for expansion. For each additional unit of capacity we had at Des Moines, we would save $4 in shipping costs. Right, so that's what the shadow price can do for us. Give us answers like that. Okay, so one more example. I think there's only one more. Right, the one more is in the tutorial slides. So in these tutorial slides, we have the final example of the day, which is this oil example. Now here we have 2 different types of crude oil that we are mixing together to make 2 different types of gasoline, regular and economy. Now this one is going to work like the previous one, where it's the combination that's important. Right? So our decision isn't just about the 2 types of crude oil we can buy, and it's not just about, right? It's not just about how much of those we buy, and it's not just about how much of these we produce. It's about the combination. It's about how much type X100 do we buy and put into the regular, how much X100 do we buy and put into the economy, how much X220 do we buy and put into the regular, and then how much X220 do we buy and put into the economy. We're going to have those 4 decision variables. Right, so if we set this up in Excel, right, we're going to have call this the blending problem. We can set up our 4 variables. Right, this is the regular X100 and the regular X220, and then the economy X100 and the economy X220. Okay, these are the things we have control over in this problem. Now we need to read more about the problem to understand. So we have some details for the 2 types of crude oil. Right? They have 2 ingredients that are important to us, ingredient A and ingredient B. And they have a price. $30 and $34.80. Let's keep reading. The weekly demand for the regular grade of no-lock gasoline is at least 25,000 barrels. That sounds like a constraint, right? At least 25,000, that's a constraint. Demand for the economy gasoline is at least 32,000 barrels. That's another constraint. At least 45% of each barrel of regular gasoline must be ingredient A. Right? At most, 50% of each barrel of economy should contain ingredient B. Those are also constraints. For the sake of this example, we'll assume that 1 barrel of crude oil will yield 1 barrel of gasoline, right? So we're just mixing them directly. And for all of these, you should notice the units, right? The units are all in barrels. Everything's in barrels. Barrels per week. 45% of each barrel, right? So barrels are clearly going to be the units for our decision variables here. So how many barrels of each type of crude oil to buy each week for blending to satisfy the demand while minimizing the cost? There it is. That's our objective. Minimize the cost. Right? So with that in mind, minimizing the cost, we can go back and look at the cost. $30 and $34.80. So the X100s cost $30. So that costs $30, and this also costs $30. Right? It doesn't matter where we put it, it still costs $30. The X220 costs $34.80. And that also doesn't matter where we put it, it costs $34.80 no matter which product we blend it into. So our overall cost is going to be the sum product of these with these. That's the objective. Now we need the constraints. And these constraints are going to get a little bit tricky. They're going to be the trickiest constraints yet, actually. Some of them are. So these first ones are not. The demand for regular is at least 25,000. Okay, so the regular is these ones, right? So this plus this has to be at least 25,000. Okay, use our sum product in here. Right, so if we produce 1,000 of these and 5,000 of these, then we get 6,000, right? This is the total amount of regular. And that needs to be at least 25,000. That's the regular demand. Right, and now we need the economy demand. We have another constraint. That's that there's at least 32,000 barrels per week of economy. So that's here and here. And that should be at least 32,000. Okay, those ones are easy. It's the next ones that get tricky. At least 45% of each barrel of regular gasoline must be ingredient A. Okay, what's this about ingredient A? Let's go back here. These X100 and X220 have different amounts of ingredient A, 35% or 60%. Okay, so the X100 has 35%, the X220 has 60%, and our regular gasoline should be at least 45%. I'm just going to share a whiteboard here. Write this down. So the left-hand side is going to be the total amount of ingredient A in regular gasoline. And that has to be at least 45% of the regular gasoline. Right? This is what I've got. The total amount of ingredient A in regular gasoline should be at least 45% of my regular gasoline. So this right-hand side is 0.45 times the regular. Now remember I had regular X100. That was like my first variable. My second variable was like the regular X220. Those were my X1 and my X2, right? So I'm gonna have like X1 plus X2. That's the total regular. Right? 45% of the regular, my right-hand side looks like this. My left-hand side depends on the X100 and the X220. Now, if you remember what the slide said, right? The slide said that X100 was 35% ingredient A. And X220 was 60% ingredient A. Right? So if I do 35% of X1 plus 60% of X2, that will get me the total amount of ingredient A that's in regular gasoline. So this is what my constraint has to look like. Right? If you can set it up like this, then all's good, because now it's just a little bit of algebra. Right? We just need to expand this out and then rearrange. So when we rearrange, we get negative 0.1 x1 minus plus 0.15 x2 is greater than or equal to 0. Okay, so that's our constraint for the ingredient A in the regular gasoline. We also had a constraint for ingredient B in the for ingredient B in the economy grade, right? It's at most 50%, so less than or equal to 50% of each economy should contain ingredient B. Right? So ingredient B mostly comes from the cheaper oil. Right? So 55% and 25%. And the result in the economy should be at least, sorry, at most 50%. Right? So we put the whiteboard back up again. Right? Now we're considering X3 and X4, right? X3 was the economy X100, and X4 was the economy X220. And this one is 55% ingredient B. And then the more expensive one is 25% ingredient B. And we had this maximum, right? We said that the total amount of ingredient B in economy gasoline can be no more than 50% of the total economy gasoline. Right? So this is going to be very similar to what we had up here, right? This is 0.5 times the total economy, which is X3 plus X4. And then over here we have the amount of ingredient B in economy gasoline, 55% of each barrel that comes from X100. So 55% of X3 plus 25% of X4. Right? 55% of each barrel of X100 that goes into the economy gasoline is ingredient B, and 25% of each of the more expensive oil that goes into the economy is ingredient B. So we rearrange this now, right? We expand this out, rearrange, we get 0.05 X3 minus 0.25 X4 is less than or equal to 0. And that's my second, that's my last constraint. Right, so negative 0.1 and positive 0.15. I'm going to put this in the Excel and then I'll share my screen on that in just a sec. That's the first part, and that should be greater than or equal to 0. And then the other one is positive 0.05 and negative 0.25. And that should be less than or equal to 0. Right, so go back to the Excel. Right, we've got this one was our for ingredient A in regular, and this was our ingredient B in economy. Okay, so the ingredient A in regular worked out like this, the ingredient B in economy worked out like that. Greater than or equal to 0, less than or equal to 0. So now we can just use solver, right? So I'm gonna go to solver. The objective is gonna be here. I'm going to try to minimize that because that's cost by changing these variable cells to satisfy these constraints. These ones have to be greater than or equal to these ones. Add that, and then this one has to be less than or equal to this one. Okay. Make them non-negative, simplex, so that we can get reports if we want reports. We have a solution, this is good. We can get answer reports, sensitivity reports, and so on. Right, so this is what we're doing. We're mixing 15,000 barrels of X100 with 10,000 barrels of X220 to make our regular gasoline. We're mixing 26,666.67 barrels of X100 with 5,333.333 barrels of X220 to make our economy gasoline. If we do that, it's going to cost us $1,783,600. And we can look at our constraints here. Now, this one's binding. These are the same number. This one's binding. Those are the same number. This one's binding. Those are the same number. This one, that's technically not 0, but it's basically 0. So this one is actually also binding. The only reason it looks like this is just because of rounding. Because solver does round these numbers eventually. You can see it's 0.6667. It's not like a fraction. It does have rounding. And so this is going to be off in like the 13th decimal place or something. It's really tiny, but this is basically 0. And Excel knows it, right? If you go to the answer report, it tells you they're all binding. It knows there's no slack, right? Even though this looks different than that, it knows that that's binding. It knows those are really both zeros. Right, so this is what we're going to do. And we can go into our sensitivity report and start trying to answer questions like, what happens if the price of gas changes? Right, what happens if the X100 starts getting more expensive? What happens if the X220 starts getting less expensive? Right, things are going to change at some point, right? And this is how much it has to change. Right, it turns out that the X100 would have to go from 30 to 34.8, right, which is the amount of the X220 before things change. In other words, as long as the X100 is cheaper than the X220, we're not changing our decision. But if it got more expensive than the X220, we would change our decision. We would start doing things differently, right? If the X100 became more expensive than X220, then we might just buy a lot less X100. We might just buy more X220. Okay, that's what we're seeing here with this 4.8. And the 4.8 here as well. If the X220 drops, it has to drop by 4.8. In other words, it would have to drop its price to below the X100 before we would care. Okay. So that's everything. So now I think you're ready to answer the quiz questions and the assignment 4 and everything. It's all set. Yeah, you have a question? Go ahead.
Professor, can you go back to the previous Excel spreadsheet? I think it's the sensitivity
Sensitivity
for,
report?
yeah. So, for example, the line item number, sorry, on cell H9. So the allowable decrease is 53.2.
Okay,
Does that make
let's talk about that. Let's talk about that. Okay, so we have an upper bound and we have
Mhm.
a lower bound, right? And then we can just the upper bound is going to be the coefficient plus the allowable increase, and the lower bound is going to be the coefficient minus the allowable decrease, right? So
Okay.
this one, the upper bound, I just said what that means. It means that the X100 has to get more expensive by this much, right? If it starts becoming more expensive than the X220, we're going to change our decision. This lower bound says that if the price dropped, how much would the price of X100 have to drop before we change our decision? And it turns out it would have to drop not only below 0, it would have to be below negative 23.2 before we would change our decision, right? Which seems a little bit silly, but I guess something would change if they started paying us to take this oil, right? We're trying to meet our constraints. We're trying to meet our constraints in terms of we can't just make everything out of the cheaper oil because of that ingredient A, ingredient B stuff, right? Like we can't have too much ingredient B. It's a problem. We have to have a minimum amount of ingredient A. So we're not allowed to just use 100% the cheap oil, even if it's really, really cheap. But I guess at this point, if they start paying us enough, then we'll be able to change something somehow, right? But in the real world, of course, this is not realistic, right? The price isn't going to go negative for this crude oil. So when we're setting this up, if this is a real world problem, we're saying, okay, if the X100 gets more expensive, we may change our decision. But the X100 is not going to get so cheap that they pay us $23.2 a barrel to take it. So
Yeah.
it's not really going to be a real concern.
Okay. Got it. Thank you.
Okay, you're welcome. All right. Yeah, so that's everything. That's the whole course. So next week, we got test review. So if you want to know what your test is going to be like, you should come next week. All right, thanks everyone. I'll see you all next week.
Thank you, Professor.
Yeah, you're welcome.
Thank you.